Ladies and gentlemen, I want to thank Helmut Dotzauer and Bertolt Hasler for giving me the opportunity to give you a presentation today. I'm very sorry for not being able to be physically present at your conference, but obligations at my university make it necessary that I stay in Hamburg those days. But thanks to the benefits of modern technology, I can be with you and share my thoughts and experiences in implementing RED plus MRV systems with you. After the presentation, I will be available for questions and for comments. The desire to reduce emissions from deforestation and forest degradation has a long history. The decisions of the conferences from Bali in 2007 to Paris in 2015 constitute a major progress in creating the political framework for RED, but it's still a very long way to go in order to implement those political decisions into practical implementations. In my presentation, I will not present the stipulations and recommendations of, for example, IPCC on MRV systems. As the implementation of an operational MRV system is a complex task, I will concentrate in my presentation on potential pitfalls in the development of MRV systems and especially on the long-term implications of the methodologies that are introduced at the first occasion. I want to raise your attention to those problems and provide some possible solutions. You all know that the first step in applying a MRV system is the construction of forest reference emission levels or forest reference levels. We use remote sensing data to assess the development of forest degradation and deforestation in the past and during the reporting period. We then use the historic development to construct our baseline and to extend the baseline through the reporting period. Our measurement activities within the reporting period provide us the real development of forest carbon stocks, and the differences between the real carbon stock at the end of the reporting period and the baseline carbon stock give us the reduced emissions. As seen in the last slide, we know the carbon stock at time 1 and we can predict the carbon stock at time 2 according to the baseline. That means under no activities that are related to the reduction of emissions from deforestation and forest degradation. From our activities, we know that we can reduce the carbon loss, so we get, by the monitoring, the real carbon stock at time 2, which should be normally higher than the carbon stock under the baseline development. And the difference again gives us the reduced emissions. What seems to be rather simple at a first glance becomes a bit more complicated when we look at the carbon stock at time 2. Carbon stock at time 2 is assessed by a combination of remote sensing imagery and field samples. And those are subject to errors which have to be taken into account. As our estimate of the real carbon stock at time 2 is related to errors, it is associated with uncertainties. And those uncertainties have to be taken into account when deriving the accountable emission reduction. As ICP requires, you can use only the lower error bound of the carbon stock at time 2 and use this to estimate the accountable emission reduction. In the widely used nomenclature, the lower error bound is known as the so-called minimum reliable estimate. The minimum reliable estimate acknowledges the principle of conservativeness and helps to avoid windfall profits from crooked monitoring systems that use unreliable predictions. Let us now have a closer look to the uncertainties related to the estimation of emissions. Uncertainties arise from different error sources. We know the observation uncertainty, which is the statistical uncertainty that comes from the fact that we use only a small sample and infer from this sample to the entire population. This uncertainty is quantified by the sampling error, and sampling errors are for professionals easy to calculate. Another source of error is introduced by models. Models may systematically over or underestimate the real values. They might provide reliable estimates over a range of input variables, but outside this range they might provide unreliable estimates. And there is the epistemic uncertainty, which arises from the fact that we normally have only a limited set of data available to construct our models. A third source of errors are non-statistical errors. Those are errors arising from measurements, from classifications, or from calculation of values. Those errors are very difficult to quantify. How do uncertainties affect the estimation of emissions and removals? I want to give you the example of the Finnish greenhouse gas inventory, where Moni and colleagues undertook a study in order to quantify the uncertainties of different sectors. In the graph you can see emissions and removals for different sectors. Bars extending to the right-hand side indicate emissions from sources. Bars extending to the left-hand side indicate removals by sinks, namely forest biomass and forest soil. The emissions and removals are presented for 1990 and 2003, and for each estimate the associated uncertainty is given by means of error bars. The error bars specify the range within which the true emissions is likely to be located. Large error bars indicate high uncertainty. The methods applied to assess emissions and removals differ between sectors. For some sectors, they are quite straightforward. For other sectors, the methods are complex and complicated. You can easily see that the errors for estimates in the LULUCF sector are much larger than in other sectors, which means that greenhouse gas emissions and removals for the LULUCF sector are associated with high uncertainties. When you look at the forest biomass estimates for 2003, you can see that the error bar is much wider than the emissions caused by agriculture or the sector's waste, industrial processes, or fugitive emissions. The uncertainties associated with forest biomass are larger than the estimated totals and can thus even extend beyond the zero line. This is very important. Remember, the error bars specify the range within which the true emissions are likely to be located. So for the example from Finland, forest biomass is very likely to be a sink, but as the error bar extends beyond the zero line, it could also be a source. In the last slides we have seen the three sources of error. How do these error types affect our MRV systems? In MRV systems, we use different data sources which are subject to different errors. Field measurements are subject to non-statistical errors. Remote sensing analysis is subject to model errors and to non-statistical errors. And in calculations and data analysis, we are confronted with all three types of errors. Let us look at those errors in more detail. Let us first look at some problems associated with the monitoring of forest degradation by passive remote sensing sensors. Passive remote sensing sensors are those sensors that capture the reflectance of the sunlight. You see in the slide the degradation over 3 periods of time. At time 1 we have a closed canopy cover, and this will be easily detected by passive remote sensing sectors as forest land. At time 2 we can see that some trees have been removed, but the canopy cover is still closed. This will result in a situation where passive remote sensing sensors still detect this area as closed forest. The degradation will not be detectable. At time 3 we have a totally different situation. Trees have been removed so that we have now an open canopy with large gaps. Here passive remote sensing sensors will detect degradation. This slide shows the problem of so-called stealthy degradation, which leads to the fact that some passive remote sensing sensors will be able to detect degradation only at a stage when degradation is very well advanced. Let us now move to field assessments and the calculation of individual tree biomass. In tropical countries, biomass functions are widely used to estimate above-ground biomass. There are two different sets of equations. The slide shows the equation where the independent input variables dBH, wood density, and an environmental factor that describes the water supply over the year are used. Let us not further consider the environmental factor, but concentrate on wood density. We use different values for wood density, namely 0.46 and 0.65 kg per cubic meter. The resulting biomass values are plotted for a diameter range of 20 to 60 cm. The blue curve shows biomass calculated with a wood density of 0.65, and the red curve uses a wood density of 0.46. You can see that at a diameter of 60 cm, we arrive at a difference between the two curves of more than 1000 kg of biomass for an individual tree. Let us now look at the red curve in more detail. You have seen the solid red curve in the previous example. It gives the biomass as a function of the dBH and wood density. An alternative biomass equation provided by Xavier includes tree height as an additional input variable. Here you see two dotted lines. The upper one gives the biomass for a tree of 40 meters height, the middle one for a tree of 30 meters height. Again, you can see that the two types of biomass functions and the values set for the input variables result in substantial differences in the biomass estimate of the tree. Remember that in many tropical forest inventories, tree height is not measured but assessed by visual judgment, as it is very difficult in dense forests to see the upper tip of a tree crown. But here you can see how sensible the biomass equations react to differences in the tree heights. This slide presents the whole picture. We use the two types of biomass functions, wood densities of 0.46 and 0.65, and tree heights of 30 and 40 meters. With increasing diameter, the differences in biomass estimates increase. At a diameter of 60 cm, we can double the C-stock of an individual tree depending on the input variables selected. This small example shows that single tree biomass estimates can be a major source of uncertainty. What can we do to deal with the uncertainties related to biomass functions? There are several alternatives, but I just want to mention three of them. First of all, we can use the most conservative estimate. That means that we take the estimate that provides the lowest biomass values. In our graph on the picture before, this would be the lower curve of all 6 curves that have been presented. Adopting a conservative estimate is in line with the principle of conservativeness. So we tend to use a very low value for the biomass and avoid a positive bias or an overestimating of the carbon stock. The next example is more cumbersome. Before we apply the biomass equation, we conduct a trial where we assess the true biomass of trees mainly by destructive samples. We then compare the true biomass to different biomass functions and select this function that is best fitting for our true biomasses. However, this procedure will still leave us with an error of about 20%. The last alternative I want to show is subsampling. Instead of measuring time-consuming parameters on all trees on a plot, we can select a subsampling for more intensive measurements. We use this larger set of parameters to calculate the individual tree biomass by more accurate biomass functions. We then update the biomass estimates of the larger sample with the more accurate biomass estimate of the subsample in order to increase the overall reliability of our biomass estimate. We talked about individual sampling errors, measurement errors, and model errors. What we need to do now is to combine the different error sources and calculate the total survey error. An equivalent term for survey error is the term error budget. Once we calculate the total survey error, we are able to quantify the minimum reliable estimate. I want to demonstrate this by an example. Data for this example were taken from the FAO's Forest Resources Assessment. I know the figure is confusing, but we will go through it step by step. I present an example for Cameroon. The rate of deforestation in Cameroon between 2000 and 2005 was utilized to predict the carbon stock at the end of a 5-year period between 2005 and 2010, under a business-as-usual development. Under the business-as-usual development, Cameroon would reduce its carbon stock by 5.18% or roughly 1% per year. What you see are the total errors on the horizontal axis and the carbon credits on the vertical axis. These are the carbon credits that can be generated by applying a red plus scheme. Let us look now at the lowest of the 4 lines. The lowest line represents a reduction of emissions by 75%. If Cameroon is able to reduce the emissions by 75% and could assess its carbon stock without any error, the country could gain some 50 megatons of carbon credits. Let us now follow this line for a moment. If the error associated with the carbon stock change assessments increases, you can see that the carbon credits become smaller. This is due to the fact that when uncertainties increase, the confidence interval increases as well, and thus the minimum reliable estimate becomes smaller. With a total error of 4%, no carbon credits can be generated. With larger errors, there is even the chance that despite of generating carbon credits, a carbon depth is generated. If you look at the other 3 lines, you can get the carbon credits for situations where the reductions compared to the baselines are smaller, namely 50%, 30% and 10%. In the case of a reduction of 10%, even with a total error smaller than 1%, a carbon depth is obvious. This slide clearly shows that not only the amount of emission reductions compared to a baseline are essential for the carbon credits generated. The error associated with the estimate and thus the reliability plays an essential role for the generation of countable carbon credits. These findings show that we need to invest quite some work in designing an MRV system in a way that it is providing estimates of carbon stock changes with small errors. Now we have to see how we can design MRV systems in a way that they result in low uncertainties associated with the carbon stock change estimates. There are several statistical procedures available that allow to combine remote sensing data and field data. I want to discuss 2 approaches, stratification and regression estimates. From a statistical point of view, an easy procedure is stratified sampling. We use the strata of forest types derived from the remote sensing imagery. The example you can see in the slide is taken from Indonesia. The entire forest area was classified into 5 strata, which show distinct differences in the carbon stock. We then compare the location of each plot with the map of the stratification and decide into which stratum a plot is allocated. Then we work through the individual strata and take all plots within a stratum to calculate the mean biomass and its variance. The size of the stratum we get from the remote sensing image analysis. In the last step, we take the values calculated for the individual strata and combine those to get the respective values for the total population. Remember that the strata sizes are used as weights, and strata with larger areas get a higher weight in the total population value than strata with smaller sizes. Let us have a look at an alternative sampling design. Some remote sensing technologies, such as LiDAR, provide discrete biomass estimates. We can then set up regression functions that link field data and remote sensing data. As remote sensing provides more points with biomass values, we correct those values by the average difference that we observe on points where we have both remote sensing and field-based assessments of biomass. The similarity of remote sensing and field-based observations are quantified by the coefficient of determination. If it has a value of 1, both observations are identical. If it is 0, then no similarity at all exists between the Earth observation and the in situ assessments. We can now check if stratification or regression estimates provide more accurate estimates of biomass. I will show you now how we can assess the cost efficiency of different sampling design alternatives. Let's assume that we have a wall-to-wall remote sensing coverage and that the cost of one field plot is $500 and the remote sensing coverage costs $1 per hectare. We look at three different sampling designs: field-based samples only, that is the classical simple random sampling, stratified sampling, and regression estimates with three different coefficients of determination ranging from 0.2 to 0.9. What you see here is the standard error over the cost per hectare for all three sampling design alternatives. You can immediately see that for cost lower than $1.1 per hectare, we cannot afford remote sensing data and have to rely on field plots only. You can as well see that with increasing cost, all sampling design alternatives become more efficient. Once we can pay for the remote sensing coverage, the regression estimate with an R-square value of 0.9 is the most efficient sampling design alternative. However, with increasing cost, the gain in precision of stratified sampling is advancing much faster than for the other design alternatives. Therefore, for costs larger than $2.5 per hectare, stratified sampling might be the most cost-efficient alternative. You can see from this slide that the selection of the optimal design depends on the available budget. Let us now look at the last problem associated with MRV systems. Let's have a look at sampling at successive occasions. What you see in this slide is the situation in time 1. We have three land use classes in orange, non-forest areas, in dark green forested areas, and in light green areas which are subject to degradation activities. As we want to assess the degradation activities with more accuracy, we increase the plot density in those areas. The situation may become awkward in the second occasion. You can see that the degradation areas extended in size, which results in different sampling intensities in those areas. And you can see a newly afforested area in the formerly unforested areas in which we have not a single sample plot. A solution to solve the problem of varying sampling densities provides sampling with partial replacement. I want to show you the principle of sampling with partial replacement in the current slide. At the second occasion, we remeasure only a subset of the plots measured at the first occasion. Some of the plots we assessed at the first occasion are not remeasured at the second occasion. Instead, we replace new plots in the sampling area. This is where the name of the procedure comes from. We replace some of the old plots by new plots in successive occasions. Here we would use new plots to fill up the gaps in sampling densities. So sampling with partial replacement puts us in a situation where we can easily combat problems arising from shifts in strata sizes and allows us to verify that our samples are still representative for the entire population and not subject to any kind of treatment bias. And the good thing is, the statistical estimation procedures for SPR are easy to apply. Plots which are measured on the first occasion only are updated for the second occasion, and plots measured at the second occasion only are backdated to the first occasion. The sampling procedures are easy to apply, and they are well described in the literature. Let us sum up. We have seen that uncertainties arise from different error sources. We need to combine those error sources in order to come up with the total survey error. Reduction of uncertainty is carrying a cost. The more reliable our estimates have to be, the more money we have to invest in our MRV system. However, from an economic perspective, a certain level of uncertainty is inevitable. Designing a MRV system can be seen as an investment. We invest money in measurement, reporting and verification in order to create benefits from accountable carbon credits. As in any investment, returns should be larger than investments. Therefore, not only uncertainty needs to be controlled in MRV development, but costs constitute a major component in the selection of the optimal MRV design as well. I want to thank you for your attention with the last slide that shows the current weather situation we have to cope with in Hamburg at the moment. I'm now available for your questions.